Let's talk about operations on matrices. The trace of an n by n matrix A is the sum of the entries along the main diagonal. We denote it by this symbol. Find the trace of this matrix? Well, it's just the sum of the entries along the diagonal. So it's going to be 1 plus 5 plus 7 plus 4 equals 17. Two matrices are equal if they have the same dimensions and their corresponding entries are the same. For example, are these two matrices equal? No, they don't have the same dimensions. We can add two matrices with the same dimensions. We add them element-wise, as you'd expect. For example, let A equal 1, 2, 3, 4, B equal 5, 6, 7, 8, find A plus B. We just add element-wise. So it's going to be 1 plus 5, 2 plus 6, 3 plus 7, and 4 plus 8. In other words, we get 6, 8, 10, 12. Let A equals 1, 2, 3, 4, B equals 5, 6, 7, 8. Find 2A. That's going to be twice A. We just multiply all the entries in A by 2. So we get 2, 4, 6, 8. Let C equal 1, 2, 3, 4, 5, 6. Find the row vectors and the column vectors of C. The row vectors of C are 1, 2, 3, and 4, 5, 6. And the column vectors are just going to be 1, 4, 2, 5, and 3, 6. Before we define the product of two matrices, we need to learn how to take the product of a matrix and a vector. We define the product of a matrix and a vector in an unusual way. So the product of this matrix and this vector looks like this. Again, it's going to be the first row of the matrix times the column. Basically, it's rows by columns. It's like you're taking the dot product of a row and a column. So it's going to be 1 times 10 plus 2 times 20 plus 3 times 30. And that'll be this first entry over here. Next, you take the dot product of the second row in this column. So it's going to be 4 times 10, 5 times 20, 6 times 30. And then lastly, the dot product of this row and this column. So 7 times 10, 8 times 20, 9 times 30. We end up with 500. Why do we do it this way? One reason is that we can use it to solve systems of equations. For example, represent the system of equations x1 plus x2 plus x3 equals 4, x1 minus x2 minus 2x3 equals negative 7, 3x2 plus x3 equals negative 1 as an equation involving a matrix. So again, these are the coefficients of x1, x2, x3 in the first equation. And then, so when you take the dot product of this and this, you just end up with 1x1 plus x2 plus x3, which is what we want over here. And that's going to equal 4. So really, you can represent this system of equations using this matrix equation. In the same way, the dot product of this with this is going to give you 1x1 minus x2 minus 2x3, and that equals negative 7. And in the same way, this will give you 3x2 plus x3 equals negative 1. We want to define the product of two matrices A and B in such a way that AB times x equals A times bx. Here A and B are matrices and x is a vector. So in other words, we want some sort of associativity. The way to do this is that the entries of AB will be the dot product of the rows of A and the columns of B. Here's why. Oh boy, this is like an end-user license agreement, so don't be too intimidated by it. This is important though. If A is an m by p matrix and B is a p by n matrix, then you can multiply A, B together and you get an m by n matrix. So again, notice that these two have to be the same if you're going to multiply them together. And the result is what's left over, m and n. A times B, now again, this seems incredibly confusing. We'll see a much easier way to evaluate this in a subsequent video, but I just need to tell you this. AB, the matrix product, the product of these two matrices, is going to be AB1, AB2, ABN, that's it, where B1, B2, blah, 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 B sub n are the column vectors of B. Why? Here's why this is what we want. If x is a vector, Bx is going to be x1, B1, plus blah, 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 plus x sub n, b sub n. If you were to work this out on your own, you'd see it. Thus, A times bx is going to be A times x1, b1, plus blah, 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 plus x sub n, b sub n. In other words, we can break that up using distributive properties. So it's A x1, b1, plus blah, 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 plus A x sub n, b sub n. you can pull out the x sub i's. You get x1 times ab1 plus blah, 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 plus x sub n times abn. In other words, you can rewrite this as ab1 dot, 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 abn times x. If you were to work out the details, you'd see that that's the case. And this is going to be ab times x if we define ab as ab1, ab2, dot, 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 abn. We'll see a much easier way to calculate this in a subsequent video.